Hello all, welcome back. This is our day 2 and today we are going to discuss about cross entropy loss function, right? Cross entropy loss function. Okay, so before that, let's review what we have already discussed in day 1 perceptron. So what we have said, suppose there are 4 input and one computational layer, right? Computational block. So what happens? This inputs are summed over and one output is generated. Okay, so based on this output we give the level as 0 or 1, right? So let's write this. So now instead of one computational block, if there is more than one, suppose 3 computational block, right? So yeah, and the same input is getting inside this computational block and it is generating a number n1. It is generating, the second block is generating a number n2 and the third one is generating n3, right? So out of this n1, n2 and n3, whichever number is the greatest, suppose n2 is the greatest among n1 and n2 and n3, right? So we say that this input belongs to n2 class. A quick uh, reminder that this all inputs are pixels, right? I hope you remember our input was MNIST dataset. Okay, so what we can do, we can keep this entire input as one block and call it as input layer. Okay, we can keep all this computational block in one single layer and call it as a computational layer, computational layer, right? So our new block diagram will be like, yeah, this is input layer, this is computational layer, and this is our output, right? And this output will be a vector. Okay, so let us define one more term, loss function. Okay, so what is a loss function? A loss function actually defines, in layman language we can say, it is how bad is our outcome, right? So suppose, for example, suppose our output, we are assuming we want to get as 1 but we get 0.9. So how bad it is? 0.1 time. But suppose we want to get 1, but instead of this we get 0.7, right? So this is much more bad than this one. So our loss function will be more for this and less for this. Okay, so okay, a quick recap what I have said. Let's take another color. Yeah, so yeah, right. So for updating parameters, uh, you may remember that our parameter is capital Phi, right? For updating the parameter, we have some rules, right? And if we are using this rule, this is known as gradient descent learning rule. What? Gradient descent learning rule, or simply gradient descent learning. Okay, where this is learning rate, our capital L is loss function, right? Loss function. In some books you may find L is written also by this form, because L is ultimately dependent upon the parameters. Okay, so finally let us define what is softmax and why we need this softmax. So yeah, what you can observe that here in this formula it is a differentiable equation, right? So the L, this L, learning loss function, by the way, this learning rate is a constant term, right? And this is a function. This L should be continuous and smooth function, right? Or else it will be not differentiable. So, but in the case of perceptron, what we have discussed above uh, in the first lecture, it is not a continuous function because the updates are like step type, so and not a continuous one. So we cannot use that loss function and we need to find some other loss function. Okay, so softmax is that type of loss function. Okay, the formula of this softmax, uh, okay, let us first understand this. Xi. So this is actually a softmax function. Okay, So it is just a softmax. It is not cross entropy loss function. Okay. So what we are actually doing using this function is that we are converting a vector x, okay, into a probability distribution. We also say it is a class probability. For example, uh, the x can be anything. Okay, suppose this 3. Then minus 1 will be e to the power minus 1 by e to the power minus 1 plus e to the power 0 plus e to the power 1. Okay, so this will be suppose a number n1. Similarly, for 0 it will be minus 1 0 plus e to the power 1. Suppose this is n2 and n3 will be 1 e to the power minus 1 plus e to the power 0 plus e to the power 1. That is n3, right? So yeah, and n1 plus n2 plus n3 will be 1, right? So we have converted a number to a class probability. So now n1, n2 and n3, n1, n2 and n3, right, is in between 0 to 1, and n1 plus n2 plus n3 equals to 1. Okay. So finally define our cross entropy loss function. Okay. So x. So x phi x. The formula is minus of ln x. Okay. So what I have written. Okay. This is a example x will x. Okay. This one is the parameter. This is the probability distribution. Probability distribution. And we have used natural log minus natural log. You may argue that why we are using this logarithm. You can think that ln of 1000, okay, and ln of 100 differs only by one step, right? Okay, 10, 100, 1000. This all differ by only one step. But actually the difference is almost 10 times. So you may say that we should not have used that logarithm term because the higher loss are penalized lesser, right? For example, if the loss is around 1000 and 100, the penalized uh, thing will be only one step, but in reality it is about 10 times more. But the concept is uh, see, this is the probability distribution, right? So its value will be from 0 to 1, right? So, and we all know that log for 0 to 1 is huge. Okay, so you can see that it should be like this. Okay, and here from 0 to 1, uh, 1 here, 1. The change is huge. So we have used this log term. Remember one more thing, that it is for one hot encoding. That means all the true level is given by 1. So whatever class is true will be 1, and all the false level equals to 0, right? If it was not one hot encoding, the formula, this one, would have changed, right, to calculate the entropy, cross entropy. So that we will come in later class. Okay. Yeah, one more thing, the concept of logit. Logit. What is this logit? Nothing but uh, yeah, this x. Okay. So all the logits are represented by vector L, and it is L1, L2, Ln, right? And this L is nothing but the input xi. So that's I think that will be enough for this class. Uh, okay, so one more thing before we wind out. Uh, yeah, this one. Our target, our main target is to reduce this loss, right? Capital L. So suppose there is only two parameter, phi 1, phi 2. Okay, and this two parameter is used to change our class output. So this is suppose phi 1, this is phi 2, and this is our loss function. Okay, so this is L. So we are changing phi 1 and phi 2 so that we may reach the minimum loss. Okay, so the parameter phi1 and phi2 value we will be changing, right? Suppose in this entire plane we will move in such a way that we reach this minimum loss point. Okay, so this is accompanied by this formula. Okay, the step size is given by this learning rate. uh, okay, that's enough for this class. Let's meet in next class. Bye.